Hello and welcome to this video about eigenvalues and eigenvectors. In this video we'll prove this theorem about eigenvectors and eigenvalues, that this determinant is equal to 0 if and only if this eigenvector of A is in this kernel, and this eigenvector has to be non-zero. I decided to call this playlist Eigenvector Proofs rather than Eigenvalue Proofs, because eigenvectors are the more fundamental quantity and define what eigenvalues are, despite eigenvalues being easier to find. So I'll just remind you of some of these things that we'll be using. We'll let vector v be an eigenvector of matrix A. When it's multiplied by A on the left, it is the same thing as multiplying it by a scalar, because this doesn't change its direction. This can be expressed by this equation, that multiplying matrix A by vector v is the same thing as multiplying a scalar lambda by v. This scalar called lambda is the eigenvalue corresponding to this eigenvector. It must be noted that most vectors aren't eigenvectors, and so don't have a corresponding eigenvalue lambda that does this. So lambda is the eigenvalue corresponding to the eigenvector v, or we could say that they correspond to each other. Let's look at an example of this. We'll set A to be this matrix, and this is an eigenvector of A. We'll multiply them together using matrix vector multiplication, which eventually gives us this vector v multiplied by 5. We could write it out as 5v. So then we could say that 5 is the eigenvalue that corresponds to this eigenvector. So to prove the main part of this theorem, we'll prove this first, that this statement is true. After we prove this, we'll substitute the expression A minus lambda I back in for B, and thereby prove the main part of this theorem. Now to start proving part A of this theorem, we'll prove it in the forwards direction first, and suppose that this determinant is 0. So B can't be invertible because of a theorem that we've proven in a past video. And so then the reduced row echelon form of B can't be the identity. So this matrix RREFB must contain a mixture of pivot and free variable columns. And so it must contain at least one row of zeros. The existence of free variable columns implies that there must be a vector that multiplies on the right of this matrix to give the 0 vector. There must be a sequence of row operation matrices such that this equation is true, because we used row operation matrices to get matrix B in reduced row echelon form. This is actually the reverse of this. We're using these row operation matrices to get the reduced row echelon form into the matrix B. We're arranging it like this to more easily do the proof. So if we multiply B by V, we'll get this result, which will give us a string of matrices multiplied by the 0 vector, which will give us the 0 vector, which is a property we've proven in a past video, and is easily shown to be true for finite matrices. So this vector v must be in the kernel of B by definition. Now to prove this statement in the reverse direction, we'll assume that v is in the kernel and is non-zero. So this statement is true because this is what it means to be in the kernel of a matrix, that multiplying the matrix by it gives us 0. So this equation is true because applying the row operation matrices to both sides gives us this. This means that this matrix can't be equal to the identity. And because it's a matrix in reduced row echelon form, and it's not the identity, then it must contain a 0 row. So the determinant of a matrix in reduced row echelon form that isn't the identity is 0, because it contains a 0 row, and this applies to matrices that have 2 or more 0 rows. So now to find out what the determinant of B is, we'll expand out B like this, with the product of its row operation matrices and the reduced row echelon form of B. We can separate this determinant into the product of two determinants like this. And one of these determinants is 0 because we've already calculated it before. And multiplying this other determinant by 0 obviously gives us 0, so the determinant of B is 0. So that proves part A of this theorem. So now to prove the main part of this theorem, part B. So all we have to do is substitute this matrix in for matrix B into part A, and we've proven this theorem. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.